All right, so the focus of this lesson is energy and power. So I'm going to go over the difference between energy and power, how they're related, but how they're different. Also, how power use impacts energy use, and give you a few concrete examples of that. So energy, and this is a review from a previous lesson, so I'm not going to go over this in detail. Remember, energy is the ability to do work, but in a more practical sense, it sort of causes things around us to happen. So anything that you see happening or perceive as happening, it requires energy to do, whether it's the sound of my voice, to see some light, to feel air against your skin, um, you name it. Anything that you can perceive requires some energy to do, okay? So we also, if you recall, I want you to keep in mind that energy is an amount of something, so it's a discrete quantity. We can measure energy, and we can have more energy, less energy, and so forth, okay? And so remember, I went over the examples of the difference between the amount of energy in a little toothpick versus a couple of cores of wood, or a single gallon of gas versus a bunch of gas, okay? So remember, energy is an amount of something. We can measure it. We can use more of it or less of it, and we can also quantify it. Also review the BTU, or the British Thermal Unit, is our basic unit of energy in the US, and it's defined as the amount of heat required to heat up 1 pound of water, 1 degree Fahrenheit. Um, This is really important in understanding energy movement, energy management, and how energy moves in and around a building. And again, if you want to visualize what 1 BTU is, it's if you would take a wooden match and burn it all the way down, you would release about 1 BTU of heat. Okay, so then we talked about unit conversions, um, and there's a number of energy units. Some are more specifically defined, like 1 kilowatt hour is equivalent to exactly 3,412 BTUs and change. 1 BTU is 1,055 joules. And then we have some other units that are not technically energy units, but we treat them as energy units when we're dealing with energy use in buildings, like a CCF, or 100 cubic feet of natural gas, a gallon of gasoline, a gallon of oil. So they all have equivalencies. And remember, one of the keys here is that you can convert any unit to any other unit if you know that conversion factor. Okay, so that's the basic review of energy. So now we're going to go over power. So energy is the ability to do work. So power, if you remember from some of the readings or videos, is the rate at which energy is converted, okay? So energy tells you how much of energy you have or use, how much energy you convert. So it's a quantity, it's an amount. Power is a rate. So power tells you how quickly you are converting energy from one form to another, okay? So it's a rate, which means it's per unit time. So power is energy per unit time, okay? So you can actually use the equation, and we will use this equation to do some calculations and some variants of this equation. But it's important to remember, just from a sort of practical or a descriptive standpoint, that power is energy per unit time, how quickly you're converting energy from one form to another. And just like everything has energy, we can analyze the power use of anything. So we can analyze the power output of a battery, how much power the human body is requiring to use, how much power the Earth is hitting, or how much solar energy is hitting the Earth, or how much power we're using on the Earth, how much power a furnace is using, so how quickly it's burning through energy, how quickly a light is using electricity, how quickly a building like the Stanton campus is burning through energy. So we can, just like we can analyze the energy content, energy use of anything, we can analyze the power use of anything. But the key to remember is that power is the rate at which energy is converted, okay? So let's look at a couple of examples. So furnaces are rated in BTUs per hour. There's a sort of an asterisk there that I'll get to in a second. But they're rated in BTUs per hour. So take a second to think about what you think that means. So BTUs per hour. So the BTU per hour rating tells you how quickly it converts the chemical energy. In this case, this is an oil furnace, okay, but this applies for a natural gas furnace or propane, any other type of furnace. It tells you how many BTUs per hour that this furnace will burn through. So, we're inputting, in this case, oil, and we're getting heat out of it. So it basically tells you how many BTUs per hour of oil you can burn in that furnace. So this is a power rating. So I want you to take a second to think about why this is a power rating. It's not an energy rating, it's a power rating. And it's a power rating because it's energy per unit time, right? So BTUs per hour, excuse me, a BTUs per hour, a BTU is energy, hour is time, so energy per unit time. It tells you the rate at which it's burning through energy. Just to be very clear, so you understand the terminology that's normally used, usually they'll be expressed, an MBH means 100 or 100,000, or excuse me, 1,000 BTUs per hour. So a 100,000 BTU per hour furnace would usually be referred to as a 100 MBH furnace, just so you know. Sometimes they'll use 100, instead of BTUs per hour, they'll use BTUH or simply BTU. So if someone says I have a 100,000 BTU furnace, they really mean BTUs per hour. Secondly, again, we'll address this in more detail later. So this tells you how many BTUs per hour it's burning through, so how much you're putting into it. However, you will get less out of it. Okay, so it does not tell you the output, it tells you the input, and you will always get less out because of the inefficiency of the energy conversion. So let's go over another, So just to sort of clarify here, so we know that a BTU per hour is power because it's a rate. And so it follows that a 200,000 BTU per hour furnace should burn through fuel twice as fast as a 100,000 BTU per hour furnace. And the same 200,000 BTU per hour, 200 MBH furnace should use fuel 4 times as quickly as a 50,000 BTU per hour furnace. So again, the reason that I'm pointing this out, the power rating tells you how quickly it's going to burn through energy. So this furnace is twice as powerful, quote unquote powerful, as this furnace, which means it'll burn through about twice the oil in this case per hour as the smaller one. The output should be about twice as much as well. And same here, it should be about 4 times for the second example. It should be about 4 times the output, but it depends on the efficiency. Okay, so let's do another example. So electronics, lights for example, but TVs, whatever, microwaves, radios, vacuum cleaners, they're all rated in watts. So watts is actually a power rating. And I want you to think about why this is a power rating. So a watt is a joule per second. That's how a watt is defined. Okay? So knowing that it's a joule per second, why is that a power rating? And the answer is, just like BTU per hour is power, joule per second is power because a joule is energy, a second is time. So a watt is a unit of energy divided by time. So this can get confusing because the watt obviously does not clearly indicate that there's a time component in it, but it's implied, okay, because that's how it's defined. So this is really important. The reason I point this out is because we will use watts a lot in this class, and watts are really important to understand in terms of energy in buildings and energy in general, okay? So if you want to think of it another way, however, whatever helps you remember it, you can think of, so if I use 100 watt hours of energy over the course of 1 hour, okay, so that's energy divided by time, that means I'm using 100 watts on average over that hour. So it's just really important that you remember watts are power and watt hours are energy. That's something that I'll ask you many times throughout the semester, but it's very important to remember. So practically speaking, if you think about the power rating of a light, it's telling you how quickly it's converting the electrical energy into, well, it's mostly converted to heat, but it's converting electrical energy at a certain rate. And so a 100 watt light should use electricity 4 times as quickly as a 25 watt light, right? So 100 watts, it just tells you how quickly it's going to burn through the electricity. And a 25 watt light, on the other hand, should use electricity about half as fast as a 50 watt light. And so this is why it's always recommended to replace any incandescent lights in your house with either a CFL or an LED, because an equivalent, 2 lights that put out the exact same amount of light, a CFL is about 4 times less power, which means it uses electricity 4 times more slowly, or in other words, an easier way to think of it is that this incandescent, to get the same use out of it, will use 4 times the amount of energy as the CFL. So let's look at a little more specific implication here. So remember, power is energy divided by time. So we can use this as an actual mathematical formula. So if you do a little bit of algebraic rearrangement here, what would the formula for energy be? So energy is power times time. This is really fundamental, really important to remember, especially from an energy management perspective. If we're looking at how much energy we're using and we want to conserve energy, the power and the amount of time is really important. So this is a really fundamental equation that we'll use over and over. So energy is power times time. So let's apply this in a pretty simple way. So if we want to determine the energy use, okay, of a 100,000 BTU per hour furnace that's used for 10 hours, how many BTUs will I burn through? So remember, energy is power times time. So I just have to multiply my power rating, BTUs per hour, times my time in hours. So if you do that, hours cancel out and you're left with BTUs, so that's 1 million BTUs. Now let's look at a 50,000 BTU per hour furnace for the same amount of time and see how many BTUs that would burn through. So feel free to do that on your own. But if you put the equation in there, pretty simple, 50,000 BTUs per hour times 10 hours. Again, the hours cancel out. So 500,000 BTU per hour. So here is where it really sort of, where the rubber meets the road, right? If I have a less powerful furnace, okay, so a half as powerful furnace is going to burn through about half the energy over the course of the same amount of time. And so that's a really important implication of knowing the relationship between energy and power. So let's look at the same thing with light. So if I use a 100 watt lamp for 10 hours, how much energy do I use? And again, we're just going to apply this equation. So power in watts times hours in time. You multiply those two together and you get 1,000 watt hours, which is all equivalent to 1 kilowatt hour. We'll go over that in a little more detail later with kilowatt hours and megawatt hours and so forth. But the point here is if I use this 100 watt incandescent for 10 hours, I'm going to use about 1 kilowatt hour of electricity. So now if I replace my incandescent with a 25 watt CFL, use it for 10 hours. Again, the math is really simple. Multiply them together, and I'm using 250 watt hours or 0.25 kilowatt hours. So getting the same amount of light for the same period of time, I use about 1/4 of the energy because the power is 1/4. The power rating is 1/4. Okay, so hopefully that helps make sense, and we'll do these calculations more as we move forward. So I just want to illustrate a little more of the relationship here. So in this chart, you can see here's the unit on the left, and I want you to press pause and think about whether these units are energy or power, and then see if you can convert that from this rating to a wattage rating. So go ahead and press pause, and then press play when you're done. So a joule, remember, is the international unit of energy. A BTU is the international unit of energy. Okay, so these are both energy. Anything with a watt is power. Power, watts power, kilowatt power, another watt is power. And then remember, energy divided by time is also power. So these are all power ratings. So if you think about how many watts these are, right? So some of them are straightforward, right? So 1 watt is 1 watt. 1 kilowatt is actually 1,000 watts. Again, we'll go over this in more detail soon. 25 watts is 25 watts. 100 watts is 100 watts. This one gets a little tricky. Maybe we'll do this a little bit later. But you can convert from BTUs per hour to watts. This is power, this is power, and remember, you can convert from one unit to any other unit of the same type if you know the conversion factor. And this is actually the conversion factor between watts and BTUs per hour. So you can convert power to power. So if I put horsepower up here, you could convert that as well. Okay. However, you notice here, you cannot convert directly from a joule to a watt or a BTU to a watt. And why is that? Because they are both energy. Okay? You cannot convert from one unit to another type of unit without adding in this case time. So in other words, I cannot convert directly from any energy unit to any power unit because they're not the same type of unit. Now, if I add the time component, then I can do that. But just be very, very careful with that. You cannot convert BTUs to watts. It's impossible. If you add the time, you can, but direct conversion, there is no direct conversion. That would be like trying to convert, I don't know, miles to miles per hour directly. You can't do it unless you add the time component. All right. So really important, you cannot convert one unit into another unit if they are different types of units. Okay, so that wraps up this lesson. So we went over what the difference between energy and power is, how power and energy are related, and also how power rating or how power impacts energy use.